To review the setup of our sampling distribution of proportions, this is going to come through with categorical data. So whenever we collect data that's in words, things like that, where we're taking proportions, this will be making where we can create a distribution of these proportions from samples. So the setup of what we went through in this simulation, we're going to have our population data, which is going to come through as just a population proportion, some proportion that we expect to come through. So it's going to define some number that we expect. And then with this proportion, then we take samples. So take a sample of size n, and once we take that sample size, we collect this sample proportion that's coming through. And then we want to do this infinitely many times. Continue it until we get a distribution of all these different p-hat values. And what we should see come through is a nice bell-shaped curve. Exactly what we want. So with this bell-shaped curve, if we imagine that this was a dot plot filled with all these little dots, each value in here is a sample proportion from a certain sample size. So with this, once we have this, we want to understand the center and spreads, then we can start calculating probabilities. So the center, which is the average of these sample proportions, that's always just going to be equal to our population proportion. So you can just grab that value. And then our standard deviation, that we need to calculate by taking the square root of p times q divided by our sample size. And just as a reminder, q is just 1 minus your proportion p. So where this will describe our bell-shaped curve, now we can start answering questions about probability and cutoff points. And what's often going to come through in the wording here is looking for what is the probability some percentage of a sample of size n, and then has some behavior. But it's looking for the probability of a percentage, seeing some percentage come through. More than that percentage, less than that percentage. It's the idea of this percent of a certain sample size. That's what's going to create our distribution of proportions. So before we can use that bell-shaped curve, we need to check those conditions. And just as a reminder of the conditions that we need to check, we need independence, making sure each of the results are independent of each other, or you can use that 10% condition. Randomization, we should be taking random samples, and again, sometimes we have to assume that. And then our sample size condition, which is also called our success-failure condition, but making sure that if you take our sample size times our proportion p, that should be more than or equal to 10. Also, if you take the sample size times 1 minus p, or the value of q, that should also be more than or equal to 10. Once we pass those conditions, we can use this bell-shaped curve and start calculating probabilities. So let's go through our example. So we're given a packet of seeds, and it says there's a 92% germination rate, and there are approximately 160 seeds in each packet. So we have here, if they're putting that on the label, that's going to be our population value. So we have this population germination rate of 0.92, so 92% of the seeds. And then we need the opposite of it, which you just take 1 minus that 0.92, which is a 0.08. And then we have our sample size, and that within one packet, we're looking at 160 seeds. So discussing the conditions that we need to check. Independence. So, like, if one seed germinates, does that change the probability that the next one does? Probably not. This scenario, there could be argument that it's not independent, like if they're coming from the same packet of seeds, maybe there's some influence there that if they're coming from the same spot. What we could use is 160 seeds is less than 10% of all seeds out there, so we can assume independence. So we're just going to assume this is okay. Same thing for randomization. We're also going to assume this because when they're taking their sample, well, first of all, it's not very random if it's coming from the same packet, and it doesn't clearly state that our sample's random, but we're just going to assume that to move forward with this problem. So sometimes that'll happen with these questions. And then checking our sample size, this we can actually calculate, so taking our sample size of 160 times our value of p, and we want to take 160 times our value of q, and calculating those, just making sure that they're both over 10. So this is more than 10, this is more than 10, so we meet that condition as well. So while if this was a formal report, maybe we would say something like we want to be careful of independence and randomization, that since those aren't clear, maybe we don't have a bell-shaped curve, but we're going to move forward with it anyway. But we definitely meet the sample size condition. But ideally, we want to clearly meet all three conditions. So defining the sampling distribution, we have our variables that are variables representing the proportion of 160 seeds that germinate. So we want to find this distribution for how these proportions behave. And for that, we need to figure out how do they average and what's the standard deviation. So the average for these proportions should just be equal to our population proportion. So we just copy down that 0.92. For our standard deviation, we need to calculate, take that 0.92 times 0.08 over our sample size of 160. And that's going to give us a standard deviation of 0.0214. So our sampling distribution model, we know it's normal because we are assuming we passed all these conditions, and the center of it should be at 0.92, and the spread is described by that 0.0214. So what you can do is get an idea of our number line, and then we're going to have a bell-shaped curve centered at 0.92, and just to get an idea of the numbers above and below, moving by one standard deviation or two in both directions, to see where we expect to land. We expect to land close to that 92%, maybe a little above, maybe a little below, kind of changing by about 2% in each direction. So now that we have this distribution, we can find what's the probability more than 95% of the seeds, or even better would be to say of the 160 seeds. This idea of having a percentage of a sample size. That's really going to connect to these sampling distributions of proportions. So with this, we want to use our distribution from up above. So we want to use that center of 0.92, standard deviation of 0.0214. And with this, look at more than 95%. So the idea of landing at 95% here, and what's the probability of being above? So we're going to look at x being more than or equal to 0.95. And that's going to give us, from whatever technology we use, 0.0805. So for our wording, we have this probability. So there is an 8.05% chance, so that's our probability, that, and then we go looking at the wording of the question. What we wanted to find is this probability that more than 95% of the 160 seeds will germinate, so we can just kind of copy that down, that more than 95% of the 160 seeds will germinate. And my word of warning with these is that it can get confusing having the two percentages, but these are formed in two different ways. This 8.05% is a probability. It's a percent chance. This 95%, this is a proportion of a sample. It's taking a percentage of a sample size. So just be careful knowing the difference between those two. When you create these sentence answers for sampling distributions of proportions, you're going to see two percentages coming through. They just represent different things. That's it for our sampling distribution of proportions.